This is Mr. Seta. I want to talk about Chapter 19, Acids and Bases. And I'm just going to go over how to do some basic calculations and how to identify an acid or a base. So this is Chapter 19. You want to make sure you've read your chapter. Okay. So if I had, in general, if I have an acid, well, let's start off with water, H2O. And I have a double arrow, means this reaction can go back and forth. The one hydrogen can go from one water to another. And so if this accepted the H, this would be considered a base. And if it accepts an H from the other H2O, that becomes H3O. And your base after it accepts an H is called a conjugate acid. Now that has an extra H. The donor of the H would be considered to be your acid. If I remove an H from H2O, I'd be left with OH, and that would be my conjugate base. Now, in an equilibrium, we're not really going to cover this, but we can define a ratio of the products over the reactants, and we call it a K. And the K for water, it's you take the concentration of your two products, and it would be H3O, and brackets around it means concentration, and you multiply them times OH. Okay, and these two are liquids. In a K, we don't put liquids in the expression. This is aqueous, this is aqueous. Usually only things that are aqueous and gases. We don't put solids and liquids in it. This number is a constant, and it's a very small number, meaning that out of all the water in a glass of water, only a little bit becomes acid and base. And as much acid as you make an equal amount of base in neutral water. Well, this value is 1 times 10 to the negative 14th. Okay, now if these two things are equal to each other, and if I call them x, that would be x squared. And if I found out what the value was in neutral water, I would take the square root. So the square root, the x, the H3O, which is equal to the hydroxide, and this would be in neutral water. This K would then be 1 times 10 to the negative 7th molar. So how much acid is in neutral water? 0.1, 2, 3, 4, 5, 6, 7 molar. That's not a lot. Okay, so it's a very small number, but the K expression, if this is true, this is true. This is a constant number. So if I added extra acid to keep this constant, the base would have to go down. So the acid and base are inversely proportional. And if I was to increase the base, then the H3O would decrease. In the equation, that's kind of called Le Chatelier's principle. If I increase the H, the reaction shifts to the left, and it causes the OH to decrease. So it causes the reaction to shift to the left. Okay. Now, so these two are the same. 1 times 10 to the negative 7 equals 0.001. So as one goes up, the other goes down. And identifying conjugates. So the conjugate base of an acid. Okay, so I'm going to give you acids. So if I give you HF, H2CO3, um, any acid, um, H3PO4. If I ask you what the conjugate base is, all you have to do is take away a hydrogen. So if HF is an acid, its base, the base of HF, is just F. So if I looked at HF, the H part is the acid, but take that away and that's considered to be the base of it. If I look at water, H2O, this is where acids and bases get their name. If I take the H away from water, I'm left with hydroxide, OH, and that's a base. That's the foundation, the base of water. So H2CO3, if I ask you that acid, the conjugate base is just to remove an H. And if you remove an H, it picks up a -1 charge. Okay. Phosphoric acid, the conjugate base, H2PO4, -1. Now, if I gave you, these things still have extra H's. So if I said, hey, let's look at H2PO4, -1, what's the conjugate base of that? I can just take away another acid, HPO4, -2. Okay. Proton. And the definition of a Bronsted-Lowry acid is a proton donor. The definition of a base is a proton acceptor. And so a proton is a hydrogen ion, H+. Okay? And so we have a few terms we can use. A polyprotic acid. It has more than one hydrogen. So example of polyprotic acids would be like H3PO4, and specifically we'd say it's a triprotic acid. H2SO4, there's two H's, so a diprotic acid. The word monoprotic, mono means one, so if I tell you have a monoprotic acid, it would be like HCl, just one H. Okay, so polyprotic acid, monoprotic acid, protons H+, and here's how we get conjugate acids, conjugate bases from the acids. Let's do the opposite. Now, there's another term I can show you right here. H2PO4 could be considered to be a base, but it also can be considered to be an acid. So it can gain an, because it has the ability to go back and gain an H and to lose another H. That term is amphoteric. And I'll start off by like my first equation. This is the autoionization of water. So autoionization of water. Okay. Water in this case acted as both an acid and a base. So, give you another definition. An amphoteric substance, amphoteric. This is something that can act as both or either an acid or a base. Example, water, H2O. H2O can gain an H to become H3O. And in that case, if it gains an H, it would be a base, and it would produce a conjugate acid. Or H2O could act as an acid, lose the H plus, donate the H plus, and then you're left with hydroxide. So that would be your conjugate base, and now it's acting as an acid. Most acids, well, all acids have H as part of them. So if you want to find an amphoteric acid, you can take a polyprotic acid like some of your polyprotic acids I just mentioned. H3PO4, H2CO3. Okay. I'm only going to use weak ones because strong ones won't go backwards. So if I take the conjugate of these, it'll be amphoteric because it has an H that it can gain and it has an H that it can donate. So along with water, you could have taken H away, HPO4, -1 with a 2. I can take another H away from that, HPO4, -2. Take away an H from carbonic acid, HCO3. And all these three things have the ability to be amphoteric. So one of your assignments is to identify acids and bases and conjugates. Let's just pick out HPO4 So if I take HPO4 -2, and I add that to water, and since these are all aqueous solutions we're talking about, they're always in water. Okay, this could donate its H, and every time you're doing conjugates, and every time you're doing conjugates, you always want to. I always like to write this little arrow with an H plus. If it's going in this direction, then that makes the HPO4 an acid. That makes the water a base. And in my conjugates, what's left of the acid, it donates an H, so it's PO4 -3, just phosphate, and that'll be the conjugate base. On your worksheet, you can just start calling it a CV. Okay, when the H gains an H, it becomes H3O, a conjugate acid. And so that's how you do that little trick. Now, if you look at your conjugates, since this is an equilibrium and a reaction can go this way, or it can go backwards. In reverse, if I say, hey, I'm going backwards, to go from H3O to H2O, you have to donate a hydrogen. The PO4 accepts it to become HPO4. And there's your definition, Bronsted Lowry. An acid, an H plus donor gives the H plus, and the base receives it. Okay. Now, or because this is amphoteric, this could have happened also. I can take my HPO4, I can put it in water, and in this case, the H could also go towards it. If that happens, now here's water acting amphoterically. Water is now an acid. Now the HPO4 is acting as a base, and your products will be different. If this receives another H, then it's H2PO4. And then this donates and it produces OH. The H2PO4, the conjugate of that base, is your conjugate acid. And the conjugate of water is hydroxide if it acts as an acid. So it's conjugate base. And that's an example of amphoterism. Okay. If I took fluoride, just fluoride salt, like sodium fluoride, and I put it in water, it would react with the water. Now I give you these reactions, but if I looked at this, the F cannot be an acid. There's no H to donate. So the water has to act as the acid. It donates the H to the F. That makes F negative a base. it's the base of hydrofluoric acid. That makes water act as the acid. On the other side, I get hydrofluoric acid. So the conjugate of that base is my conjugate acid. And then water had donated the H, so what's left of it is hydroxide, which would be my conjugate base. If this reaction went backwards in this direction, then the H would donate the H to the OH. Same thing here, if this one went backwards, that would donate another H to make that water. And so that's how you do your conjugates. And this is the assignment, and I just did that example. I've done a few of these. Not really. I've only done one of those. But you want to go through and identify these as acids, bases. That'll be on the left. And the thing you always want to look at is you want to draw a line between these two. If you see the water became OH, so for that to become OH, this has to donate the H. That makes water here the acid. That makes the HCO3 become the base. And if it accepts an H, my other product better be H2CO3, H2CO3. So the conjugate is a conjugate acid. That's your conjugate base, what's left of the water. And if I went in the other direction, these arrows should all be double arrows. So in the other direction, it would go that way. So that's how you do these. Okay. Naming. I'd ask you to name HCl. I'll do another example down here, HF. An ide in acids becomes a hydro blank ic acid. So HCl, just like HF, would be called hydrofluoric acid. I change the ending to ic and I add hydro to it. Hydroiodic acid. If it says hydrofluoric acid is HF. Now, 8 ions, if you add an acid to it, they become ic acids. And ites, ions plus H, they become OUS acids. So I'll give you just a couple more examples. If I had something that's up there, H3PO4. So PO4 is called phosphate, ATE. So H3PO4, the name's going to change to phos. It's a little different. They add 4, but the ending is ic acid, phosphoric acid. If I drop an oxygen off this, H3PO3, PO3 is phosphite. Well, the name of this would become phosphorous acid. In naming, ic is always a higher number, 4 is a higher. OUS is always a lower number, 3 is lower than 4. That's where it gets that from. So for all these that just say phosphoric, you would say phosphate and then add, phosphate has a -3 charge, so you'd add 3 H's to it. Nitrate comes from nitric comes from nitrate. Nitrate equals NO3, -1. So with that nitric acid, you would just add 1H, and that would become nitric acid. So that's just a little refresher on naming acids. You can use the internet to help you with any of these. The back page I'm going to show you on a separate video how to go from pH to POH to H3O to OH. It's not too bad. And that's all I'm just going to do basic acids.